Well, good afternoon. I'm sorry it's 6 minutes late getting started, but I was talking with Dr. Bryant about something, and then next thing I knew it was after 2:30, and I hadn't gotten back by my office to pick up my the book, to exchange books. So I just got back from doing that. If I sound a little winded, that's why. But anyway, let's get started from the current slide. By the way, it is 2:36 on a Monday afternoon, the 28th of January 2019. This is supposed to be differential equations class, and right now I'm the only one in the room. And we have a total of, 6 students registered for the class, and always, I mean, we've had 2 days perfect attendance, 1 day just too short, and then more recently only 2 people here, and now 0 people here, so hopefully some will be coming in soon. Okay, so let's get started where we left off last time, if it will ever get there. Nothing's happening so far. Okay, here we go. Let me get my pen picked up, and sorry about the cough and the hoarseness. This morning I was sitting in the office working, and all of a sudden, just like my head just started draining like crazy. I'd been perfectly fine up till then, and so all the rest of the day I've been having drainage problems, and my head's clogged up and can't talk well. But anyway, my memory from last time, we finished 1.1 finally, and we're now in 1.2 initial value problems on page 15 in chapter 1, Introduction to Differential Equations. So initial value problems. We're often interested in problems in which we seek a solution, y of x, of a differential equation, but we know something about that y of x. That y of x satisfies certain prescribed side conditions. Okay, that is, conditions that are imposed on the unknown function y and its derivatives at some number x. Okay, now quite often, and they call these initial value problems, quite often our variable is not x, or you can name it anything you want to, it could be x, but quite often it's t, time. A lot of differential equations deal with time. So your initial situation, you can measure that. You know, what is your initial situation? Maybe initially you're dropping a ball from a height, so you know its height, you know its initial velocity is 0, you know the acceleration due to gravity is g, you know certain things about the problem there. Those would be the initial conditions at time t equals 0. Other times it doesn't have to be at any time, or it could be some later time. Maybe you caught a ball and you knew at that point what its velocity was because you had a radar gun behind you right before you caught it, and you know exactly what its speed was. So that may be the time, 4 minutes after, or 32 seconds after the ball was hit or thrown or whatever, or a half a second after the ball was thrown. Whatever it is, it doesn't have to be initial. It doesn't have to be t is equal to 0. It could be any kind of fixed point or time or whatever that you know something about that problem. Okay? So the conditions are imposed on the unknown function y of x and its derivatives at some number or value x sub 0. It doesn't have to be 0, but it could be any value that you do know about. On some interval containing, and that interval is usually called I, containing that x sub 0, the problem of solving the nth order differential equation subject to those side conditions is specified at that value x 0. So here would be a sample. It says solve this nth order, and we'll use x as the independent variable, y as the dependent variable, is some function of, and just like we have done before, x, y, y prime, y double prime, y triple prime, dot, 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 all the way up to and including y, the n minus first derivative of y. Never the nth derivative of y, because that's what you're looking for. That's what the problem is. So you could have any or all these variables in there, okay? But if you did have those, you need some, you might say, controls. Subject to, and these would be your initial or other conditions. Subject to y at x0, that some value x is equal to some value y0. One or more of these could be 0 or not. They're just values. Your y prime at that same value, you know to be y sub 1. Your y double prime at that same value, x sub 0, you know to be y2. Your y triple prime, I left off the y triple prime at that same value, x sub 0, you know to be y sub 3, and so far on up to and including the nth minus first derivative of x at x sub 0. Derivative of y at x sub 0 would be y to the n minus 1. Okay? So you have a function of x and y, and then all these derivatives of y up till, but not including the nth derivative of y. That's your function. Okay? The initial condition, the side condition, the thing you know at some point, x sub 0, some value for x, you do know, all these things are there, okay? Your y value you know, your first derivative you know, your second derivative, your third derivative, up to and including the n minus first derivative. You know at that point x0, okay? And these values here, y0, y1, y2, y3, y sub n minus 1, these are all arbitrary constants. They can't have x dependence, they can't have y dependence. They're numbers, they're constants, they have some value. Now in reality, they're quite often dimensioned, like one would be the y might be a displacement, the y1 might be a speed, the y2 might be a velocity. They could have various physical meanings with units and stuff, but they're just numbers, just numbers with those units or whatever. So this setup that we have here is called your nth order, because that's you got nth order ordinary differential equation, but the nth order initial value problem. And they put initial value hyphenated problem. From now on, I'll call it an IVP. Okay. When I was in grad school, I was a member of a Christian organization called InterVarsity Christian Fellowship, and they had a publishing arm that was called InterVarsity Press. So I'm thinking of IVP as being InterVarsity Press. In this course is initial value problem. Okay. The values are called the initial conditions. These values here, the y1s, y0, y1, and all those are called your initial conditions. Sometimes it's called ICs. Okay, initial conditions. So solving an nth order initial value problem, such as the one listed here, frequently entails first finding the n parameter family of solutions, just like we've been doing before, of the differential equation, then using the initial conditions at x0 to determine those n constants in the family. Because if you had an nth order differential equation, you'd need a C1, a C2, a C3, a C4, up to C sub n, as those parameters. Those are your n parameters. And you then plug in these values to get what those C's are. So, goodness gracious. Now, not only is my throat dry, but my eyes are so dry I can hardly stand it. Of course, I'm reading the book right over where the fan blows out of the computer, and that's probably what's doing it to my eyes. But boy, that makes them hurt. I mean, it stings because it's hot air and it's drying them out like crazy. Okay. So here will be a problem. I don't think I can keep it on this page, so let's clean this page and go to a new page. Here's your differential equation. dy dx is equal to f of xy. Nothing very specific, very generic here. Subject to, and how many initial conditions do you need here? First order, you only need one. So that would be y at some value x0 is equal to some value y0. Okay. Now, this is a first order initial value problem, IVP. Okay? Now, in your book, they show, let's just imagine that you have your y-axis here, your x-axis here, and you're dealing with an interval that goes from here to here. Let's say A to B. And this is your interval. X equal A to x equal B is your interval. This differential equation. And these are potential solutions to it. One here, one there, and one here. Or something probably wouldn't be that weird. Let me clean that top one up a little bit. Okay. Something like that. Okay. If this is the value x equal x0 right here, then if you knew that the y0 happened to be here, then that would place you, I didn't quite get it right there. That would be the curve that you would use. The others are all solution to the differential equation. Every one of these will solve the differential equation depending on what c's you have in there. But this one right here will fit that curve. That point will be on that curve. So that's the solution to that differential equation with those boundary conditions, initial conditions. Now, if you had a second order, oh, we've got someone here. Turn on the second light if you will, not the one that's that. Good. Glad to see you. Oh, what's that?
I got ethnic traffic. Where is it?
I don't know. Today's the 28th, and we have the 29th, 30th, and the 31st of this week. So Muhammad is here. Yeah, I do not know where folks are. Now I can understand maybe tomorrow, possibly Wednesday.
Well, Birmingham City School is already closed.
What's that?
Birmingham City School just closed.
School's closed for tomorrow, all day? Okay. Is a good chance we will follow, but it's not guaranteed. So keep watching out for it. Are you on that Cougar alert? Okay. It should show up there. I'm on it, but unfortunately it's our home phone that I have listed on it because that one we can hear throughout the house. And unfortunately it died. Something about our line somewhere, it's so scratchy you can't hear anything. And sometimes you don't even get a dial tone. Other times you do, but it's messed up. And we called it in more than a week ago, and it's still going to be more than a week before they get to it. So, and it's covered in our bill, but they're taking their sweet time. So I've got to check my computer, so I hope we don't lose power, because without power I can't do my computer. And we wouldn't be able to do the phone either because it's on a mobile device. So it's or a station, and the station would go out. So anyway, I've got to keep an eye on it, and we'll power's out. But they say there's not a good chance of power going out because there's not that much wind and there's not going to be ice accumulation on the power lines. So there shouldn't be that problem. Just the cold, but the ice on the roads, that could be the problem. And probably will be.
If I'm driving, I'll be in trouble because my small car, the tire is broken.
Well, yeah.
I drove to the ground.
Yeah. Well, those are not the best things to be even on wet roads, but certainly not on icy roads. And the other issue is it's supposed to start raining sometime this afternoon or evening. And the temperature is going to start dropping, and it's going to continue to drop. And it just depends on whether the rain stops before the temperature falls below zero. If we get a good wind then that could dry off the roads more quickly, there may not be a problem. But the odds of that happening are not good. The odds are it's going to continue raining until it turns to snow, and at that time the temperature is going to keep dropping, so all the moisture that's on the road is going to freeze with snow on top of it, which is going to be even worse. You won't be able to see the ice even, so it could be pretty hazardous tomorrow.
They say the rain may start at midnight.
The what?
The rain, they say, is going to start at midnight.
Yeah. The rain starts at midnight.
That's what the weather said.
Yeah, or the winter weather starts at midnight. I think they said the rain should start earlier, but the hazardous conditions start around midnight. The temperature dropping with the moisture and the snow. Anyway, whatever it is, it could be bad before in the morning. It may not be, but the odds are it probably will be. And then the sort of the best thing that's happening, what's the temperature outside now? Close to 60? 61. So with that kind of temperature now, it's going to take things a while to get very cold. So it may be that there won't be that much ice, but the thing is, it depends on when the temperature starts dropping and how rapidly it drops. That will be a big factor in it, and how low it goes. They were calling for it to be in the 20s tonight. I heard at one time 28, another time 26. If it gets down that cold and there's still moisture on the road, no matter how warm it is today, that stuff's going to freeze. So that's going to be bad. Now, the thing about tomorrow, it may not get much above freezing tomorrow. They're calling for it to, and if it does, it could melt some of it. But if we don't get a good strong wind with the melting, then when it drops tomorrow night, and tomorrow night's supposed to be in the 20s, it could be it'll all freeze again. And that could even be worse than the first one, because then it'll be perfectly slick. And you won't be able to see it either. So that could be bad. So,
That's the dangerous one.
what's that?
That's the dangerous one.
Yes, it is. So watch for it both tomorrow and Wednesday. Check your Cougar Alert, check the weather, check the messages across the screen on television. Check whatever you can to see it. Don't drive on bad tires in this stuff. It's just not worth the risk. Even with good tires, it's not good to be traveling on ice. So be careful for that. All right, I had already started talking on page 15. I don't think you have a book yet, but I've already been through. Oh, let me turn on. When nobody's in the room, I usually don't waste the bulb. You already fixed the light, so it's fine. Though I already got a slide or two done, and I was on the bottom part here. This was just a representation of and this is sort of bad with the light coming in. It's probably going to be hard to see it taking a long time for the bulb to warm up here. Here it comes. Okay. If you have a differential equation, first order, ordinary differential equation, dy dx is some function of x and y. Okay, that gives you a family of curves, depending on your constant of integration, your c. And this will only have one c in it. Okay. Okay. But,
Where's the C?
what's that? Well, yeah, I don't show the solution. Whatever the solution is, it has one parameter. It's called the one parameter system. Okay. Now, if you know an initial condition, okay, this is good on this interval from A to B, say, or whatever it is, interval I, and some x0 in that interval. If you go up here and find a curve that you know the y0 is there, then rather than having these various curves for different c's, like this could be c equals 0, 1, 2, 3, or c equals -4, -3, -2, whatever your c is, each one of these is a curve that would fit that differential equation given, you know, whatever the parameter is. So you have a whole family, infinite number of possible solutions. But if you know one value, at x0, y is equal to y0, then you have you know exactly which one of those curves that would be. And then it's here. All right. And that's called an initial value problem, or IVP. The IC, initial condition, that would be y at x0 would be y0. As long as x0 is any value in that. Now we call it initial value problem. I was saying this before. Coming from the physics side of things, at t is equal to 0, you know this is your position, your speed, and that kind of stuff. That's why we usually call it an initial condition. But it doesn't have to be initial. It can be any particular value that you know the other values have. That's called your initial condition, or this book actually calls it a side condition, which is a fine term. Okay, and this would be an example of how that plays out in a first order linear differential equation. It doesn't even have to be linear, just differential equation. Okay, let me draw for you their example. No, those are derivatives, regular derivatives, not ordinary. These are ordinary. We're not really going to be doing many, if any at all, partials. There will be a couple things when we'll need to take some partial derivatives, but we won't be doing partial differential equations. Okay, yeah, this is on page 15, that geometric interpretation, the first one. My picture isn't just like theirs, but it just represents. Now I'm going to erase this and show you a second order. Okay? This would be stuff like d2y, second derivative with respect to y, second derivative of y with respect to x squared, okay, is equal to, now this time it's some function of both x, y, and y prime, the first derivative, okay. Here they use Leibniz notation on this side and prime notation on that side, but that's just typically how they do it, okay. Here, to have a well-posed problem, you would need to know both a y at some x0, and we'll call that y0 just like we did before, but we'll also need to know y prime at x0, and that's going to be some y1, say, okay? So y sub 0, okay? My zeros are really poor looking, aren't they? Okay. Now, what that family of curves looks like would be something like this. Again, we're going to keep everything positive. It's just easier to do. We'll have this being our A here, and our interval here will be I, going over here to B. So I is, okay, like this. And here you could have a variety of curves, you know, again. But at any value, say x sub 0, here, you have a y sub 0 here, but we also have the first derivative of y at x sub 0 is this. So the slope here would be, let's call it m1, would be y1. You know, at that particular point, you know that. So you know the position at x0 and you know the slope at x0. This is in case you had a variety of curves that had the same x0, y0 value but had different slopes here. This picks out which curve that is. Now they drew them as if they're separate curves here, but you know, they you could have had for different parameters. This would be a two-parameter system because you'd have to have two independent parameters here to well define that system. One for your y and one for your y prime. Okay? Now the x is given to you, so you got them at x0, and then you have a y0 to correspond with that is a y prime, y1 to correspond for the first derivative at the same time. So that would be your initial condition, or side condition, the book calls it sometimes. It doesn't have to be, say, at t equals 0. It could be x equal anywhere in the interval over which it's defined. Can't be outside, of course. Okay. And they talk about them coming from the physical sciences. All right. Here's example 1. Okay, this is on page 16. And Dan, by the way, before you came in, Muhammad and I were talking. Listen up for, do you have any classes tomorrow? Okay, so you just listen up for your work. But Wednesday even, there still could be some problems. If we get significant ice, snow and stuff tonight, and it stays pretty cold tomorrow, or even warms a little bit above freezing, but it's supposed to be in the 30s all day tomorrow. But even if it gets above freezing and we don't have some drying conditions, as in wind or something like that, then it is going to get very cold again tomorrow night. If the water's still there, it could refreeze again. So listen up to see if school will be here for Muhammad both tomorrow and Wednesday, but for you just Wednesday. Are you on Cougar Alert?
Yeah, through my wife's email, but I don't have my phone.
Right. Okay. Yeah, I don't have my cell phone. I have it on my home phone, but I was telling Muhammad our phone went out about a week ago. I'm sorry, AT&T. And we have called them, and they said it'd still be another week before they could get to us. So it's so I've got to pay attention on my computer. I don't think we're scheduled to lose power because, like I said, they're not calling for there to be a great amount of wind and no ice accumulation on power lines, they hope. I don't know, y'all hope that too, on phone lines, but they're not supposed to be any. So the probability of losing power is pretty low. So hopefully everybody will be able to stay warm and get information they need. So here's example 1 on page 16. It refers back to problem 45 in exercise 1.1, the previous section, but since we haven't done that, you were asked to deduce that y is equal to c e to the x is a one-parameter family of solutions for the simple first-order differential equation y prime is equal to y. Okay? That's a pretty simple system, right? Now, if you think about it, what is about the only function you know whose first derivative is the same as the function?
Constant.
Second?
Nothing more than be constant.
No, that would be 0. Unless the constant were 0, derivative of 0 is 0. That would work. But the derivative of any constant, 7, 14 pi, derivative of that is still 0. Okay, so that wouldn't work unless it was 0. And that's a trivial case. Okay, so we won't mess with that. The only function whose derivative is itself. My favorite one to take a derivative, or an integral of, e to the x. The derivative of e to the x is e to the x. Okay, so that's, I guess, how you deduce that y equal, but because it's a first order differential equation, you need to put a parameter in there, c e to the x. Because when you take a derivative of that, y prime, that would also be c e to the x, and those are equal to each other. Okay, so that is a one-parameter family of solutions for the simple ordinary differential equation y prime is equal to y. The solutions for this family are defined on the interval minus infinity to infinity. So your interval here is minus infinity to infinity. Anything within that, it still works, because E is a well-defined function. No limitations on it. Now, if we impose on this an initial condition, say y at some value, say 0, is equal to 3. If that was our initial condition, and you only need one because it's a first-order differential equation, well, then plug this in. Y at 0 will be 3, and that would be c times e to the x equal 0, right? Well, what is e to the 0? E to the 0. 1, of course. So then you have c is equal to 3. So now you know your exact differential equation, y is equal to 3e to x. And you can draw the graph of that. X equals 0, not 1, but 3, 1, 2, 3, okay? There's your value, and then the function goes like this. That's it. There's an infinite number of possibilities. At c equal 2, it would be going like that. C equal 1 be going like that. 4 like that. This is the one you have. That is the one and all. And by the way, you have negative 1. I mean, you have other c's that could go negative on you. That's the one where c is equal to 3. When c is equal to 3, you'd have y is equal to 3e to the x. So you would be vertical stretch up to 3 from 0, the x-axis, x-intercept, okay? Now, if on the other hand, you said, subject to the condition that when y is equal to y of 1 would be equal to negative 2, then you would plug in negative 2 is equal to c e to the minus 1, and then your c, what you do is multiply both sides of the equation by e, and that would give minus 2 e to the first is equal to c. And e is 2.7 blah, 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 blah. Multiply that by minus 2, and you're down here somewhere. So they show in the book somewhere down here at y is equal to 1, x equal 1, your y is down here at negative 2. So I didn't plan well enough ahead to show that one well. But that would be one of the curves that is curving down, because you see your c is a negative number then. And that's going to take you downstairs. Plugging that back into your equation, your solution, y is equal to minus 2e x plus 1, okay? Because you got one e from your constant and the other e from your variable, so x plus 1. They didn't write that out for you, but it would be the case. I'll try to. I didn't draw mine well enough, so here's what it'll be. There's the one where c 0, 3 is on the curve. Here's the one with 1, negative 2, which the overall scale here would be on the curve. This has a negative coefficient, that's a positive coefficient.
How come they're showing negative 2ex minus 1?
What's that? Oh.
On example 1, they've got x minus 1.
Okay. Oh. Okay. Yeah, I'm sorry. I was doing it fast in my head. Yeah, because you plug in c is equal to okay, here, okay, I hope I got that part right. C is equal to minus 2e, so you have y is equal to c, no, instead of c you put minus 2e. I can't get it. Yuck! There we go. Okay. Minus 2e, e to the x. Okay. I don't know how they got that, because I think mine's right. Let's see. Or did I do it backwards?
Because if you're finding a differential, you have to...
Yeah, well, I may have plugged in backwards here. Y of 1 is equal to minus 2. So here we would be minus 2 is equal to, oh, that's where I messed up. When y is equal to 1, that's supposed to be a plus 1 there. Okay, yeah. So then you divide, and this will be, that's a minus 1 there, and then that creates a minus 1 there. You're right. Good catch. So does that mess up? There, I think that's, no, that was the plus. Yeah, so that's y is equal to minus 2 e to the x minus 1. Yeah. Sorry about that. All right, I was doing too fast. All right, and the next example illustrates first order initial value problem. This example, notice how the interval depends on the initial condition, y0. Okay. So, again, they're referring to a previous something another. Problem 6 of exercise 2.2, no, referring to something we haven't done yet. You'll be asked to show that the one parameter family of solutions of the first order differential equation y prime plus 2x y squared equals 0. Okay. Now, time out. Oh, there we go. All right. What kind of differential equation is this? 3 classifications. Ordinary. Oh, you said second order? Second. The derivative, which derivative it is? Maximum derivative is 1. Yeah. First order, ordinary. Yeah. And what's the third classification? Either linear or nonlinear. What is this? Nonlinear. The x squared there means it's nonlinear. If that had been an x, linear. This is nonlinear. We haven't gotten into why and what difference that makes, but this is just the name of it, nonlinear. Okay. Now, that they were given to us. Okay. It says to show that a one parameter family of solutions is this one. Y is equal to 1 over x squared plus c. Okay? First order differential equation, you only need one parameter system. Now, we need to show that is indeed a solution for that one. What's one thing you got to do? What's the Jesus answer?
Differentiate.
Take it right. Y prime. Ooh, boo hiss. Let's rewrite this as x2 plus c to the minus 1. I like taking derivatives of that more than I do the quotient rule. So this is a power rule. So what would that be? Negative x squared plus c to the to the negative 2. But then we got a chain rule, which I think was where you were starting, which is times 2, not x squared, 2x. Derivative of the inside is 2x. So I'm going to put the 2x out here. Okay, so I'm going to rewrite this now back in the form we had before. It would be a minus 2x over x squared plus c squared. Okay. Now, let's see if this does fit up here. This will be a minus 2x over x squared plus c squared plus 2x times 1 over x squared plus c. Okay? Is that, oh, wait, squared, yeah. So square this and square that, because that y squared. And sure enough, this is minus 2x over x squared plus c squared, and this is plus 2x, because 1 squared is 1 over x squared plus c squared, and that's equal to 0. Here's the question mark. There we see. Yes, it is. So, this is the solution for that, a one-parameter solution. Okay. That's what we'll be asked to do in exercise 2.2, which is a chapter away. Okay. If we impose the initial condition that y of 0 is equal to minus 1, okay, what would be, let's see what it's asked us to do. Okay. So what you do then is take this y, this is y of x here, is equal to 1 over x squared plus c, and plug in a 0 for x, so y of 0 would be what? Go back.
1 over c.
1 over c, okay? But we were told that's equal to minus 1. So what would c have to be? Minus 1, okay? So let's plug that in. Y is equal to 1 over x squared minus 1. There would be our solution for that differential equation. Okay. But, here's the but here. All right. If you were to graph this, what you see obviously is you have two places where this is not defined, right? This is 1 over x plus 1 times 1 over x minus 1. Or you could leave them both. You didn't have to put two different ones. But anyway, x cannot equal negative 1. X cannot equal 1. So you have two vertical asymptotes here. Okay? Now, we also, if you remember back from pre-calculus algebra, you know that the ratio of the leading terms gives you a horizontal asymptote, and that would be 0. As x gets very, very, very large, positive or negative, then 1 over x squared is very, 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 very close to 0. So you have a horizontal asymptote at the y-axis. Okay? So that then tells you that you could have a solution here, a solution there, or a solution, let's see, where does it intersect here?
Looks like you intersect somewhere around
When,
0.5.
yeah. Well, when x is equal to 0, y is equal to 1 over c, and we just had this, so it's going to be at minus 1. So this is going to be the part down here. Okay. Now, which of these curves must be That's the only one that fits, because x can't be 0 here or here, only here. And this would then be your curve. So not only does your variable tell you which curve you have, it may limit the interval over which the whole thing is defined. It can't be defined for x is less than -1. Never can be defined at x equal -1. It can't be defined for x positive 1, greater than positive 1, or even x equal to positive 1. Only place it can be defined is here, because it's the only place it can be 0. Now, I didn't show you exactly how those curves came out, but I just knew from experience that's how the curves are going to be. Because when x is in between plus or minus 1, this part is always positive, but then when you have the c is -1, if c is greater than x, and so you have to be in between plus or minus 1 for c to be greater than x, but then it's all negative. Okay? And the closer x is to plus 1 or minus 1, the more it's going to is that right, or does it turn the other way?
No, that's right.
Yeah, okay, it is right. Okay. That's the only possibility. So, all right, Peyton's here.
And I examined the mountain broken in to make it all the way down.
Oh, okay. Are you undilated yet?
Yeah, I hope so.
Okay. Because you're in the sun over there. Okay.
Yeah, thankfully it's sort of cloudy.
Yeah.
So,
Yeah. And again, I've just been warning everybody, because you got classes tomorrow and Wednesday. Please check.
yeah.
Are you on Cougar Alert?
Yes.
Yeah. And also check TV and other things too for any announcements.
And I'm going to go pick up my glasses.
What's that?
I'm going to pick up my glasses.
Oh,
So,
tomorrow? Oh boy, yeah. My wife's supposed to have a dental appointment in the morning, and she said, "Oh shucks, maybe I'll have to miss it." You know, so not particularly fond of the dentist. Okay, we just did example 2. We're talking about initial value problems and how the initial value will pick out which curve it is when you have a family of curves. But in this example, it also showed you, it also picks out the interval for you, because the only place this one was defined at y is equal to 0 was for that, the two pieces of the function here, where you have rough asymptotic plus or minus 1, minus 2 plus 1. These parts go up here, this one's down here. This not only defined which family of curves, it showed you which interval it had to be on. You had to be in the same one here for it even to work. Okay. Now, we now emphasize the following 3 distinctions. Considered as a function, the domain of 1 over x squared minus y squared is a set of real numbers for which x is defined, and that would exclude x equal minus plus 1 and minus 1. So that would be any old curve that looked kind of like that. Okay? Considered as the solution of the differential equation, for that particular differential equation, that could be taken to be any interval over which that's defined and differentiable, and that would be either the part from negative infinity to minus 1 to plus 1, or plus 1 to negative infinity. All exclusive of the open intervals there, okay? And then consider a solution for the initial value problem that then fits it down there, that curve, and only that piece of the curve, okay? None of the other pieces would fit. So we're ready for example 3, which is bottom of page 16. Can I move on? All right. Okay. in example 9 of section 1.1, which we had a few days ago, I guess, or maybe even last time, we saw that here was a solution. Well, I like to write the differential equation first. For this differential equation, x double prime plus 16x is equal to 0. Okay? Now just to fill you in on possibilities here. Earlier, we had one, x prime is equal to, y prime is equal to y, okay? That had to be e to the x. That's about the only possibility you had. With a constant c, that would do, okay? Now you have something whose second derivative is a negative multiple of your first derivative, okay? Now, those functions, if it was x squared minus 16x equals 0, then you could say x squared is equal to 16x. Well, that would be an e function again, but it would be e to the fourth or something like that, because you do it twice and you get 16. But this is a plus here, so this means...
It's going to be hard because...
What's that?
Negative, even if it's a negative now, it won't work.
No, that won't work either. What will work are your sines and cosines, because the derivative of sine is cosine, the derivative of cosine is minus sine. But the second derivative of a sine would then be a minus sine would be a minus cosine. Second derivative of a minus sine would be a minus cosine. So yeah, this is going to be a sine or a cosine. So sort of get used to that. And sure enough, that's what ours turned out being. The solutions were x is equal to c1, that should be a subscript 1, sine of 4t plus c2 cosine of 4t, unless I got them backwards. No, they put the cosine first. It really doesn't matter, but I'll put it the way the book did. Yeah. It really doesn't matter which one you put, but I'll put them the same way the book did. They're just parameters. I could change my parameters rather than this, but I'll put it the way the book did. Okay. Doesn't matter. Okay. Two-parameter family of solution. Yeah, it's got to have two parameters. It's a second-order differential equation, so it's got to have two parameters. And there they are. Okay. And I hope you see, if you take the derivatives of it, y prime would be minus c1, 4c1, because the 4 from here, 4c1 sine 4t, plus 4c1, c2, cosine 4t, right? That's the first derivative. Okay? Second derivative would be a minus 4 times 4, 16 c1 cosine 4t, minus 16 c2 sine 4t, which is exactly the opposite. Minus 16 times this one, so in other words, this one's with minus, that one's with a plus, and they add 0. So, yeah, we can verify that pretty easily and quickly, okay? Now, it says find a solution of the initial value problem. Now, what are we going to have in the initial value problem? X at some value must be some value. But that's not all. What's the second thing we'd have to have? X prime at the same value, these two have to be the same, is equal to something else. Okay. This one would be a value, that would be the slope, okay, you might say. The velocity, you might say, or something like that. Well, what are those? Pi halves. X at pi halves, they say is negative 2, okay? And x prime at pi halves, it has to be at the same place, and that's equal to 1, okay? They just have to be real values, okay? But the x values must be the same. So what do we do here? We plug in. Plug it in, plug it in. So x is equal to C1 times cosine of 4 times pi halves would be 4 times pi halves, 2 pi, plus C2 sine of 2 pi. Okay. What is cosine of 2 pi? 1. What is sine of 2 pi? 0. Okay. So this gives you, and since x at pi halves is minus 2, you have minus 2 is equal to C1. Because cosine is 1 there, and we don't have any information about C2. Okay? So let's take that and plug it in. So x is equal to minus 2 cosine 4t plus C2. It doesn't matter. I'm plugging in now, but you could have waited to do this, but sine of 4t. Okay? I miswrote that and y'all let me get away with it. That was x prime. Wasn't it? No, that was x. Wait. Where did, we haven't differentiated. That's what we're going to do here. Sorry about that. No, we haven't differentiated it. So that was right. Okay. That's what we're going to do now, is differentiate this. X prime is equal to what? Negative 8, isn't it? Negative 8. Oops. Sine. No, then it's not negative, is it? It's 8 times the cosine. What's wrong? Ugh. Hit the wrong icon down there. 8 times the sine of 4t. And this one?
14 minus
4t, yeah, that stays the same. Okay.
I'm going to go from 2 to 8.
Okay. Gotcha. Okay. It's minus 2 times the derivative of this. What's the derivative of that? Derivative of cosine is negative sine. No, derivative. Derivative of negative, okay, if you say it that way, that's fine. Derivative of negative cosine is sine, but then you also have, and so you would have a 2 in front, okay, but then your chain rule, derivative of this is 4, so 2 times 4. The cosine gives you, derivative of cosine is minus sine, so that loses the minus sign. You would have a 2 here, but you'd have a 4 from the chain rule. So that's that. Second part. What's the derivative of that? Now, the derivative of the sine is cosine, not negative cosine. Derivative of cosine is negative sine. That's why it changed this sign, S-I-G-N sign. But this one doesn't change.
It's going to be C2 cosine.
Yeah. C2 cosine 4t. But what else? 4. Yeah, you have to have the 4 for the chain rule. Okay? Now, so that's what x prime is. But x prime of pi halves, so let's plug in pi halves. X prime of pi halves, this would be of any x, any t. I wrote t down here. Pi halves, I did, is equal to 8 times the sine of
14.
pi halves times t is, pi halves is t. I'm sorry. Okay, let me get this cleaned up again. This is x prime at any t. Is that plugging in a pi halves there? When t is equal to pi halves, what's 4t? Same as it was before. And T is pi halves. 4 times pi halves.
It's gonna be 2 pi.
2 pi.
2 pi, okay. Plus 4c2 times the cosine of 1, okay, because 2 pi, by the way, cosine of 2 pi, which is 1, okay. And what sine of 2 pi? 0. So this gives us, and we see that x prime of pi halves is 1, so 1 is equal to, that goes away, 4c2 times 1. So what is c2?
1/4.
Is equal to 1/4. Okay? So our 2-parameter solution, no longer parameters, we actually know the values. We have x of t at any value t is equal to c1, which is minus 2 cosine of 4t, okay, plugging into this, okay, plus c2, which is 1/4, times the sine of 4t. And you don't need a plus c or anything else. You have plugged in the parameters, plugged in the initial conditions to determine what parameters you are, so you don't need any constants in anymore. Except that constant, no arbitrary constants. Those 2 constants we determine. You go back and put them in your original solution. Okay. You calculated them when you plugged in the values, but you plug them back into the original solution. So that gives us x equal minus 2 cosine 4t plus 1/4 sine 4t. That's a solution for this differential equation with these initial values, your IVP, initial value problem. Now, 2 fundamental questions arise in considering initial value problems. Ooh, goodness, we're running out of time, aren't we? Okay, here are what they are. Does a solution for the problem exist? If it does exist, is it unique? So we call this the existence and uniqueness questions, okay. For the first order initial value problem number 2 that we did before, that was the 3 pieces of the graphs, and it had the 1, we asked, does the differential equation dy dx equal f of xy possess solutions? Do any of the solutions pass through the point x0, y0? And we saw it did. One, and only one curve, and only one piece of that curve. Uniqueness, when can we be certain there is a precisely one solution curve passing through the point? Okay? Now, they're really getting picky here. If you read example 1 at the top, A, in problem 45, blah, blah, you see that y is equal to ce to the x is a 1-parameter family of solutions. It doesn't say the 1 parameter, it says a. On the B, oh, okay, that was the same one. Number 2, you'll be asked to show that a 1 parameter, again, they say a is that, okay. But 3, in example 9 of section 1.1, we saw that this is a 2-parameter system. So they're leaving it open. It's a little weasel word, but it is that. The phrase a solution is used rather than the solution. The indefinite article a is used deliberately to suggest that the possibility, not definite, but possibility, other solutions may exist. Okay. And are we going to have time for example 4? Huh? 4 minutes, let's try it. Okay. each of the functions y is equal to 0 and y is equal to 1/16 x to the fourth satisfies the differential equation. So let me start over by erasing all this. Here's the differential equation. dy dx is equal to xy to the 1/2. If you think back, I think this is the very first example we ever had, but this time we're going to give a initial value to it. Y of 0 is equal to 0. Okay. Now, they've just told us y equals 0 satisfies both of those, doesn't it? When y is equal to 0, the first derivative of y is equal to 0. In other words, y is the 0 function. It's the x-axis. Okay? Everything on the x-axis. Derivative of that is 0, because the derivative of the horizontal line is 0. And if you have x, which could be any value there, times the square root of 0, square root of 0 is 0. So for any value x, 0, that is satisfying. Okay? But another solution is y is equal to 1/16 x to the fourth. Okay? Now you could go back and plug this in, which we've done before. Take a derivative, and you get 1/4 x cubed, right? 4 times 1/16 is 1/4. And then drop that by 1 x cubed. Well, the square root of this is 1/4 x squared. Multiply that by x, you get 1/4 x cubed is equal to 1/4 x cubed. Yes, there's a solution too. Okay? So y is equal to 0 is a solution, and y is equal to this is a solution. Well, when y is equal to 0, when x is equal to 0, y is equal to 0. And when x is equal to 0, or x equal anything, y is equal to 0. So both of these are solutions to that initial value problem, but they're two different solutions. Here's one, there's one. Okay? At the point, x equals 0, y is equal to 0, both of them are solutions, but that's the only point they are. Okay? So just the fact that you know it satisfies that initial value, you still have two possible solutions. The first is called the trivial solution, and we usually just throw it out and say, well, yeah, we know that's always true. But we're interested in more interesting solutions such as that one. Okay. All right. Do we have time for the theorem? I think not. Okay. So we'll begin next time with the theorem 1.2.1 at the bottom of the page. I've got 3 marks on this page already, so let me get rid of these two so I'll know which one we're talking about next time. All right. So we made decent progress, maybe not great progress. Exercise 1.2, we only got 1 page or so left to go here. Try to do number 1, either 3 or 5, or both. Either 7 or 9, or both. Either 11 or 13, or both.
We haven't done.
Yeah. Yeah. The one we just did was similar to 15, but not the same. So you can try it if you want to, but if not, hang on. Should be able to do it after we do the rest of it. Okay. Good deal.
Some of these chapters, they have every other third answer in the back.
Oh, you mean every other odd,
Yeah.
or just odds?
Yeah, every other odd.
Okay.
Answer.
Okay.
So it would be like 1, 5.
Okay. If you have those, then do the ones that the answers are in the back. Yeah. I hadn't looked at all of them, so I didn't know that for sure. I know that when you get to the discussion problems, generally none of those are in the back, or not many, if any. So that's why I don't usually assign those. But usually the ones that have answers, it's either the odds or I didn't realize. It's almost always only odds, but now I realize from what you said is not all the odds. So
it goes from, exercise 1-1 goes from 9 to 15.
every one or a jump there when you say?
Just, it jumps. It has answers for question 9, and then it jumps to questions for number 15.
Oh, I see. So it has all the odds up to 9. Is that what you're saying?
Yeah.
Okay. Let me look at those.
And then it goes from 19 to 31. So it skips.
Yeah. But you see, oh, I see. Okay. So they didn't have 11 or 13 in that one.
No.
Okay. Yeah. There's still something similar to what we did, so I would say try them anyway. You just won't be able to. I would only try one, but you can't check your answer. But 15, there is one. And you say after 15, it jumps to?
No, 17. It goes from 15 to 17.
Oh, 15 and 17, so it has both of them. 19?
And then 31.
Okay, so it skips.
All of the 20s.
Yeah, all of the 20s. That's a shame.
Yeah.
Let's see. Yeah, I have an instructor edition. It may be that mine had, I thought I checked those early on, but I may not have been careful in my checking. I just checked a few. It looked like they all. See, I just, does your, oh yeah, it says selected, right?
Yeah.
See, 1.1. Yeah, 1, 3, 5, 7, 9. Yep, then it skips 15, 17, 19. You're right, I hadn't noticed that. I guess I just looked and saw only odd numbers back there. Yeah, well, but that seems to be the only one. No. Interesting. It seems like most of the others have more odds. I'm not going to say they don't skip any, but most of the others. I think that first one, because some of those you have to write so much down, and that may be why they left some of those off. But most of the rest of them, I was just noticing 2.1 and 2.2.
Oh, wow.
Yeah, they jump around big time. They only do big numbers in the 20s for page 44, and then on page 52 they only do small numbers. Well, no, they do more big numbers too. I'd have to look at the individual ones to see that, but I'm glad you pointed that out. So if the answers aren't in the back of the book, and you don't feel like you are confident enough with it, try some, and if you don't, bring them to class and we'll do those. But if you say, oh yeah, this is pretty straightforward, then hang with it and still do them. But yeah, we need, I can't say you're not going to have any that don't have some of these answers in the back, because I didn't check for that later. Or, I mean, similar to these. It won't be these, obviously. Okay. Good deal. Thanks for pointing that out. Sorry about that they were like that. All right, I will go on and shut this down so we can start up.